tutorial, we will implement a tile shuffle effect in Max. Before we start patching, I want to go over what we're actually trying to achieve here. So the idea is to scramble an image by generating a shuffled or permutated tile index list. Then we'll convert those indices into UV positions, and then we'll turn those UV positions into offsets. The final offsets will then be used to sample the final texture or the final image. This tutorial consists of 4 parts. In the first one, we'll get a scrambled or permutated tile list or list of indices. In the second one, we'll turn these indices into UV positions. In the third one, these UV positions will be turned into an offset. And then in the fourth one, we'll do the sampling to create the final output image. I am starting with a jit world object because we're working with textures and this will be our rendering context. Then here I have a jit.p window so we can monitor what we're doing. And this is our input video. So starting with the first part, getting the scrambled list of indices. So the idea is that if we have an input image, we want to split it into different tiles and then number them from 0 to n-1. So as this is a 2D image, we have a certain number of tiles on the x-axis and a certain number of tiles on the y-axis. Imagine we split this up into 4 to 3. So we'd have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 tiles here. So 0 to 11, which is 12 tiles. So first we need to define the number of tiles we want. So let's start with the tiles on the x-axis, so x tiles, and here we have the y tiles. So this will just be set by a number box. And then in order to create the list of indices, I want to use an USI object. So with this one, you can specify, so either you can specify the number of bangs. So if I'm putting 5 in here and then I bang this object, then I'll get, I mean, this was pretty fast, so you probably didn't see it, but if we look into the Max console, so I specified 5, so I get 1, 2, 3, 4, 5 bangs out of here, but we can also use this output, which gives us the current index. So now this one goes from 1 to 5. So we can just multiply the number of tiles on the x-axis by the number of tiles on the y-axis, use this as an input here. And if we're using 4 to 3, as I said before, then okay, yeah, so again 3, 4, then we'll get our indices out here. The problem here is that it starts with 1 and we want to start with 0, so I'm using -1 here. So now it goes from 0 to 11, which is exactly what we want. And I also encountered a problem here, as you probably saw, that so this is the cold inlet, this is the hot inlet, but either way, I want to trigger this no matter if I'm changing this number or this number. So we can do something like trigger bang integer. Oh no. So with this, we can set the cold inlet here and then also bang in here to get an output. So if I'm changing this to 4, then we should get 0 to 15. Yeah, seems to be working. Okay. Now these are just individual numbers. In order to get a list with all of those indices, we can use the object zl_group. No, that's not what I wanted to do. zl_group. We also need to tell this object the size of the group. So we can do something like trigger integer, because this will be the same number. First we have to trigger it, so again 4 and 3. And then we have our indices, and somewhere along the way I deleted this -1, but it's kind of crucial, so I'm putting it back in here. So now we have a list that is going from first index to last index, but we want to have a permutation, so we want to scramble this with each element only appearing once. So in order to do this, we can use another ZL object, and this one is called ZL Scramble. And this will give us each index exactly once, but in a different permutation, which is exactly what we want. So I guess that's it for the first part. We have a list of indices and we have a way of scrambling it. Now coming to the second part, now I want to go from this index list, so 0 to n-1, to the actual UV position in terms of a two-dimensional vector. I will show you what that means in a second. So in order to do this, I will use jit.gl codebox. And this one, of course, needs a matrix as an input. So we can say jit.matrix. Let's call this index, 3 planes, float 32. And I will set the size to 1 by 1 for now. But we'll have to change this one when our number of tiles changes. So we could do something like trigger integer. Up here, put another one here, and then use a pack object, say dim 0, 0, and now we just send the dimensions for the matrix to this pack object. This will set then the dimensions here in the matrix. Let's see if this worked. So jit.fps. Look at the dimensions, and if I change something now, nothing happened, but if I'm banging it, yeah, so seems to be working. So I will quickly make this a bit tidier. Okay, let's do something like that. Okay, so now we have a matrix and we have a list, and in order to fill this matrix with this list, we can use the object jit.fill. This needs the name of the matrix, I think. And then, yeah, let's use a jit.cellblock object. if I'm banging this, yeah, we can see the permutated list. And if I'm removing this, yeah, we can just see the list of indices going from 0 to n-1. Okay. Then we want to create our UV coordinates out of those indices. And in order to do this, I will now use the code box here. Yeah, let's call this, I don't know, new tile position. So the idea is that the UV positions rank from 0 to 1 on the x-axis and from 0 to 1 on the y-axis. I think, yeah, I will start with just the regular list, and then we can take a look at the scrambled list. Okay, so in order to turn this into our UV coordinates, I will first create a variable called x, and then we need to go from this index to our normalized x coordinates. In order to do this, we can say that we're using input 1 and only the x component of input 1. I mean, I guess it doesn't matter because all of the components are the same here, because it's only one number for all of the planes. But yeah, just to make it a bit more explicit, let's say in1.x. And then we have to use the modular operator by the dimensions of our by the dimensions of the x-axis. So this will go from 0 to 3 for all of those rows. So let's see if this works. So I will duplicate this, put it down here, bang it, and now you can see we're getting the coordinates for x, so always 0 to 3 on the x-axis. And in order to get y, we have to use the index that is coming in, and then we have to divide it by our x dimensions, because so here in this row y should be 0. So we can divide whatever is coming in here by dimensions of x. So here y should be 1. And as you can see, if we're dividing 4 by the dimensions of x, which would be 4, so 4 by 4 is 1, 5 by 4 is 1 point something, 6 by 4 is 1 point something, and so on. And then we can take the floor of this one. So what does this actually mean? So I will copy this. Then we can divide this, and then let's just take a quick look at the output we're getting here. So you can see here we're starting at 0 plus some decimal places, 1 plus some decimal places, 2 plus some decimal places. To get rid of those decimal places, we can use the floor function. And now you can see that on the y-axis, we're always going from 0 to 2, 0 to 2, 0 to 2. And then we can do something like output 1 is a vector. And then use the message plane -1, which should show us all of our planes. And then if we bang it again, you can see that on the x-axis, it's always going 0, 1, 2, 3, 0, 1, 2, 3. And on the y-axis, always from 0, 1, 2, 0, 1, 2. But we want to create normalized coordinates. So what we have to do is we have to divide x by the dimension of x, and we also have to divide y by the dimension of y. And then we can use another jit.p window to take a look at the output here. Okay, now you can see we have these normalized coordinates. And if I'm changing something and I'm doing something like 16:9, you can see that the resolution also changes here. Banging it again. Now we have this. Okay. But yeah, we didn't want this because it would have been easier to achieve this by just using the normalized coordinates we're getting anyway in Gen. But now we can use the scramble, and now you can see that we're getting permutations. So it's still the same coordinates, but at a different position, and each of them only appearing once. Okay. So now we got from our index, or our list of indices, to our UV positions. Then in order to create an offset, we need to take the positions we created here. So let's maybe call this one new position. This is the vector we just created here. And in order to create our offsets, we have to use our just normalized UV coordinates. So I will create them quickly here. So UV equals the individual cell divided by the dimensions of the whole thing. We can quickly take a look at this here. So these are the UV positions. Here we have the positions we just created, the scrambled ones. And in order to create an offset, we have to subtract our UV positions from our scrambled positions. Because then when we're sampling, we're adding what we created here to the UV positions we're using. This might be a bit confusing. I will show you what I mean in a minute, but yeah, this is the final output. Okay, coming to the fourth part, now we want to do the sampling. So in order to do this, I want to use jit.gl.pix codebox. So we'll have to turn this one into a texture. Doesn't need a name, but we need to say filter none. At least I think we do. Let's take a quick look. Okay. Yeah. Same thing as before. Now I want to use this video as an input. So we can say, let's just call this one picture in. This is input 1. And then offset in equals input 2. And let's say output 1 is picture in for now. Then we can patch this in here. Patch this in here. I will also use a texture here and specify its size. Depth 0. Okay. Now this is just the output. Okay, so now we can plug this one in here. And now we can do the actual sampling. So the output will be the input sampled with these offsets. So we can use normalized coordinates. So this one is just the output video. And then we're adding this offset to our normalized coordinates. And now it's scrambled. And as you can see here, we have to add this one to our offset. So we're using the normalized coordinates, adding the offset. So here we have to subtract it. And the thing is, we couldn't just have done it in here because we have different resolutions. So here the resolution of the matrix that's coming in is 4:3 or whatever we're using up here. And here it's full HD. So we need to do this kind of weird process of first getting rid of the original UVs and then adding them back in. Because what we're sending, so from this one, we're not sending the actual position, but we're sending the position delta. So we're sending not where this tile actually is, but where this tile is in relation to the original UV positions. Okay. So in principle, that's almost it, I guess. What we could also include here is, so because now, playing this, now it's just like switching around. But we could use a jit.slide and say slide up something like 5, slide down 15. Okay. Yeah, then we would also need, oh, sorry. I'll just make some space. In order for this to work, we need another matrix that we can constantly bang. So jit matrix, then we can use jit.bang. And the idea is that, yeah, we're sending this matrix into this one. And then this slide object will then take some time to reach the final destination. So now it's animated, which is also looking pretty nice, I think. What we could also do is create a message, set all 0, bang. So if we're sending this into the matrix, then all of the offsets will be set to 0, which should theoretically create the, or recreate the original picture. Yeah. So now we can change it, go back to the original, change it. Yeah. We can also change the resolution here, 16 by 9. Bang this again. Or make it even more extreme, making it full HD. Okay, this one doesn't work. Yeah, the problem is this one has a limit, so set a max size, so this one is the limit. So I will just put it in here, 767. This one has to be set, so let's also put it in here. So Okay, what's the output here? Okay, that's still more than the limit we have here, so let's do something like this, which also looks very nice. Okay, this can be very fine-grained. What also looks very cool is if we're just using like one dimension, so just scrambling it on the x-axis, especially with this video where we have a lot of vertical action, or something like this, 160. Yeah. Okay. Yeah, so this is essentially what I wanted to show you. I hope you found this useful. Thanks for watching.